Okay, next in the line we have Mr. Dhaneshwar Sahu from NIT Rourkela. He will be presenting his works on prediction of natural frequency. He'll be presenting his works on prediction of natural frequency of multiwalled carbon nanotube-filled woven glass fiber and metal laminated structures using artificial neural network. Over to you, Mr. Sahu.
Good afternoon to all. First, I thanks to Professor R.K. Singh sir to giving me opportunity to deliver my talk on the topic of prediction of natural frequency of multi-walled carbon nanotube-filled woven glass fiber and the aluminum-based fiber metal laminated structure using artificial neural network. Last 2 days we have we have seen many lectures dedicated to either purely fiber-based composite or metal matrix composite. So in this talk, I just cover what happens if we combine the fiber and the metal. Then what are the advantages? As a mechanical engineer, we know that we aware that vibration is a big enemy for us in structure application. So using fiber metal laminated structure, somehow we minimize the vibration structure for aerospace application. Fiber metal laminated structure consist of glass fiber and the aluminum fiber, and these are the sequence shown in figure 1. That first aluminum layer, then glass fiber, then again aluminum, then aluminum layer, then glass fiber, then again aluminum. So combining these fiber reinforced composite and aluminum, we can take advantage of robust structure and a lightweight structure. These are the some applications which are used for fiber metal laminated structure, such as that high strength to weight ratio. These properties are generally used in aerospace, automotive industry, defense and military, construction industry, renewable energy, and rail and transport. Then second property like improved fatigue resistance, these are used as mentioned, and excellent impact resistance, superior corrosion resistance as it combined with glass fiber, so we can minimize the corrosion. The objective of present work is to first we prepare the multi-walled carbon nanotube-filled glass fiber through hand layup technique. Then we prepare fiber metal laminated structure. Then performing the free vibration analysis using impact model hammer test to capture their natural frequencies. Then subsequently we perform the effect of various parameters like aspect ratio, side to thickness ratio, and fiber angle in laminate sequence of one glass fiber, how these parameters affect the natural frequency. Then finally I propose the prediction model to predict the natural frequency using artificial neural network. These are the fabrication process as shown in figure 2. Left side shows the block diagram, and this is right side shows the actual fabrication process. And the engineering constant of both aluminum sheet and the glass fiber are calculated through uniaxial tensile test, and adopted the HTM ISO standard. And as we know that the bidirectional woven fiber have similar elastic constant in both direction, either transverse or longitudinal direction. And to get accurate result and to minimize the error, I have tested 5 sample in unit in length direction and the 45-degree direction. Just 45-degree fiber direction is required, elastic property is required to calculate the shear modulus, which are calculated through Jones formula, already mentioned in Robert M. Jones Mechanics of Composite Material book. And after performing tensile test, elastic properties are shown in table 1. These properties are further used to perform numerical simulation in software, finite element software. And experimental model setup are shown in figure 4, and their frequency response function and coherent plans are shown in figure 5. Generally we use roving impact hammer test, where accelerometer is fixed in particular location and we impacted the specimen in different direction, different points, and we captured the natural, actually through experimental model analysis, the natural frequency are obtained in time domain. Then we apply in DAC system in built FFT, which is used to convert time domain frequency into the frequency domain. And also we simulate the natural frequency in Abacus software. First we create a geometry, then dimensioning the geometry, then we lay up the geometry and assemble. Then we assign the mesh size, and this mesh size is finalized through convergence study and validation study. And then we assign the boundary condition, different boundary condition. For present analysis, I have adopted 4 types of boundary condition: cantilever boundary condition, opposite side fixed, and opposite side free boundary condition, and the 3 side clamped and 1 side free, and all side clamped boundary condition. Then we assign the task for natural frequency, and these are the table 2 shows the convergence study. After many iterations, first I perform for 4x4 mesh size, then 8x8, then 12x12, then 16x16, and finally I come to conclusion that 20x20 result gives uniform result. So I adopted this mesh size, and I also validated the previous literature, natural frequency of previous literature. And then I performed the parametric study through finite element software. First I investigate the effect of aspect ratio, how aspect ratio affect the natural frequency. And in figure 8 it has been observed that when we increase the natural aspect ratio, the natural frequency for all types of boundary condition, it is decreases. Why? Because when we increase the aspect ratio, the flexibility of the structure increases, so natural frequency decreases. Same trends are happen in side to thickness ratio, as mentioned in figure 9. And table 5 shows how fiber angle affect the natural frequency, and it is noticed that when we increase the fiber angle, the natural frequency decreases from 0 to 45 degrees. Then I propose a neural network model. For that, I have taken 3 input: aspect ratio, fly orientation, and a side to thickness ratio, and my output is first 2 mode of natural frequency, where aspect ratio I taken from 1 to 5 in the interval of 1, and the fly orientation first 0 degree, 15 degree, 30 degree, then 45 degree, and 60 degree. And side to thickness ratio is taken from 20, 40, 80, 160, and 320. These are the flow chart. Figure 11 shows the flow chart. First, we start the process, then we assign, enter the input and output, then we assign the learning algorithm, then we define the activation function, then assign the neurons in the hidden layer. Then we train the network, and we check that if mean value is greater than 95, then we close up, terminate the process, finalize the. If mean value R is less than 95, then we again assign neurons the hidden layer and train the network. These are the error table where Levenberg-Marquardt learning algorithm is finalized for further artificial neural network training. It's seen that R square value regression coefficient of relation is highest in this case, and mean square error and root mean square value are lower for both training and testing. These are the regression plot and the performance plot for artificial neural network. Then after that, I have tested the 4 boundary condition for unexamined data. I am not using that data which I have early used in training. These aspect ratio, ply orientation, and the side to thickness ratio, that are completely new data, and perform prediction analysis, and also subsequently I perform same thing, same parameter I using feeding into the finite element software, and I am getting very close result. These all results are within 5%. Table 12 shows the 3-side clamped boundary condition and all side boundary condition. So finally, I conclude that for any structure, when we perform modal analysis, then all side clamped boundary condition has highest natural frequency as compared to the other, because when we increase the constraint, the stiffness will increase, which leads to higher natural frequency. Then when we increase the aspect ratio, it decrease the natural frequency. Same trend is follow for side to thickness ratio and the ply orientation angle. Additionally, ANN based prediction model is proposed to predict the first 3 mode of natural frequency, which are then compared with the FEN based software, and the obtained natural frequency from both technique like finite element method and data driven artificial neural network have less than 5% error. Thank you. Any question? Yes. Yes. Yes.
Thermal management.
Actually, at some extent, I assume that there is a perfect bonding between first I prepare the glass fiber, multiwalled carbon nanotube-filled glass fiber. Then I cure it for 2 days. Then I rub both the surface, like glass fiber, polymer composite surface, rub through MRE paper, and also the aluminum layer. Then in between there, I use the adhesive RL light for perfect bonding, as RL light shows the highest strength for metal, and as per previous research, they are also using RL light to join to layer the metal layer and the one glass fiber layer.
Have you done any study for higher temperature exposing?
No, actually, my study is basically on dynamic analysis. So yes.
You have mentioned that you have used that carbon nanotubes and
Yes,
for
sir.
your work. But I feel whenever you are going for the nano level instead of micro level,
Yes, sir.
so dynamics will change. It is not applicable, whatever applicable at micro level, and if you are going for the nano level.
Yes,
So
sir.
have you compared that thing or
No, sir.
same boundary condition?
I just follow what are the previous researchers they have done. So my main focus is how to improve the natural frequency.
That's fine. But whenever you are doing the work at a micro level and you are going shifting towards the nano level, so the dynamics and boundary conditions, everything will change. So have you tried for that?
No,
Or
sir.
just whatever a previous researcher have done, So you are accepting the same thing, same condition.
That work is based on some assumption. So that part
That level you have to go.
Yes, sir.
In the nano level you have to go.
That part I didn't study.
Thank you very much, Mr. Sahu.